compiler really care about the prototype, the variable names, the argument names in the prototypes? The answer is that you don't really care about them. Off the top of my head, I don't recall whether the uniqueness argument, the uniqueness requirement applies to prototypes as well in the spec, in the C-minus spec. I don't remember. Okay, but that's something that it's easy to look up. Either it does or it doesn't. Strictly speaking, we don't need argument names. Conceptually, we don't need argument names in the prototype, right? All we need is a sequence of types. In the C-minus language requirement, in language spec, I put in variable names or argument names in the prototype to simplify parsing, so that you wouldn't need a completely different set of parsing rules for prototypes as for. Now, I don't know whether that simplified parsing or made it more difficult. It's conceivable that if all you had was a tuple of type names, it might have simplified parsing even more. I don't remember. I don't know. I know that right now, the first time you are able to tell if you're processing a prototype or a function definition is when you see a left curly brace that begins that comes after the arguments. And maybe if all you had was a set of type names, then maybe that would not be a problem. So I don't know. But to answer your question, strictly speaking, all you care about is the type and sequence of the arguments. The variable names themselves have no significance in prototypes. But having said that, I don't recall if the C-minus language spec requires those to be distinct variable names. But certainly they don't have to match up with the subsequent function definition. They aren't required to match up. Okay, runtime memory organization. So again, context is that the compiler is generating code. It needs to know what's going to happen at runtime, what memory is going to look like at runtime, so that the code that it generates behaves the way you'd like it to. So this is typically how memory is organized at runtime. At low addresses, you have code, you have some static data, then you have the heap and the stack. Typically, the stack is on the high end of the memory and grows towards low end. The heap grows in the other direction. And this way, you have this big amount of empty memory. So if you have a program that uses only a small amount of stack space but lots of heap, you have room. If you have a program that uses only a little bit of heap space but lots of stack, you have a lot of room. This picture is misleading in one way. If you take this too literally, it's to suggest that your code begins at 0 and that your stack begins at the highest possible address. That is not true. Okay? There's stuff up here that's reserved for the OS. There's stuff down here or down there and up here that's reserved for the OS. So for example, the Linux code, I think, uses the top 1 gigabyte of a 4 gig address space for the kernel code. Okay? So this is the user code and the stuff at either end. The user code does not have access to the entire address space of a system. What a compiler typically does, and what your programs will do, is compile the program one function at a time. So it'll generate code for function 1, and then it'll generate code for function 2, and so on down to function n. Typically, the code for a function is contiguous. Okay, so this is sort of very natural, and it's a natural consequence of the fact that I'm generating code for the first function, and then I generate code for the second function, and so on. Right? So all of the code for the first function lives together. The way your compiler will work is when you get to code generation, you're processing function 1, the first function in the program. So you start reading it in, you start doing, you process the declarations, you're putting stuff in the symbol table. You start seeing the body, you do your type checking, then you generate code, then you leave the function. And that causes the local symbol to get cleaned out. Okay, stuff in the global symbols table sticks around. Then you see the second function. And something similar happens. You read it in, you do your type checking, you generate code for the second function, you leave the second function, you clean out the local symbol table. Then you process the third function, and so on down. Now, if you hit a syntax error in the 12th function, you can't undo the code you've generated already. That's okay. There's nothing wrong with that. So if you hit a syntax error in the 12th function, at that point, there's no, once you hit an error of some kind, maybe it's a syntax error, maybe it's a type error, whatever. Once you hit an error, something went wrong. You gave the appropriate error message, you do your best error recovery as you can, you stop code generation. There's no point generating code anymore because who knows what happened with the error recovery and all. That's something that you guys have encountered already, right? So you stop generating code from that point onwards. There's no point generating code. I mean, you can if you want, but it's not going to do you much good. The stuff you've generated already, for your project, don't worry about it. Okay? What happens with something like GCC is that it generates code into temp files in /temp. So it just goes and deletes that /temp file, and of course, you never see it. So it looks as if the compiler never generated any code to begin with. But the code was getting generated. It was being put into a file in /temp. OK. Now, within the function, the compiler has complete freedom to reorganize the code any which way it likes. Okay? And it turns out, and if we have time, we'll talk about this later on. It turns out that if you choose the order of the instructions very, very carefully, that can be beneficial for the instruction cache. So this can actually have a significant impact on performance. There's an interesting experiment that Rick Snodgrass and one of his PhD students and I have been doing over the semester. And this was quite surprising. What happened was, the quick summary, and we don't need to go into the details of this, but the quick summary was that we were putting we are having some code being injected into a database system. So Rick Snodgrass is a database guy, right? So he and I were doing this stuff, and we're injecting some code into the database. The hope was that by being clever about what code we injected, we would speed up the execution of the database. So databases are big old programs. So his PhD student went and made changes to all of the pieces that needed to be changed. Then we did a timing run, and it slowed down. So Rick was heartbroken. It's like, oh man, we just wasted 6 weeks of programming. So then what we did was we said, OK, let's go look at the instruction cache behavior. And we looked at the instruction cache behavior, and it turned out that there was this huge slowdown because of the particular location where some code was being placed. So what we did was we took this code that was being injected into the database, and we kind of moved it around a little bit in memory. So instead of generating the code at location, I'm just making this up, right? Instead of generating the code at location 20,000, we said, let's generate the code at location 25,000. And performance improved. So long story short, after a couple of weeks of playing and tweaking with this, we now see really nice improvements on a bunch of benchmarks. So Rick is a happy guy. So, but the moral of the story here is that this seems very counterintuitive. I mean, why should just moving the code in memory from one place to a slightly different place have a profound effect on performance? Well, that's the way caches behave. And if the compiler is savvy and collects some information and uses that information properly, it can do good things for performance. OK. So going back to activations, there are two issues that the compiler will have to manage. One is mapping source-level program names to things that exist at runtime, namely memory locations and registers, within a function. Okay? So the compiler has to manage that. And that it will do via the symbol table. So it's going to collect up stuff in the symbol table. And when you get to code generation, one of the things that it'll do is figure out the location where each variable lives. And that symbol table information will take care of this mapping. The other thing the compiler has to do is to set things up so that at runtime, the different activations of a procedure are properly dealt with. Now, this control stack exists when? At runtime. Okay, when the compiled program is executing, then its runtime stack comes into play, and functions get their stack frames pushed and popped and so on. who generates the code to do that pushing and popping of stack frames? It's the compiler, right? So the compiler has to generate code so that when the program is executed, when that code is executed, these things happen. Okay, so that's the other thing that the compiler will need to do. So calls and returns within these code will have to be handled. So what happens then at runtime is when a function is called, when it's activated, an activation record gets created and pushed. Okay, I'm deliberately calling it something other than stack frame. Okay, an activation record gets pushed, and then when the function returns, that activation record gets popped. So how is an activation different from a stack frame? Well, the contents of an activation record, which is information that is needed to manage that activation of the function. Okay, the contents of the activation record may be on the stack, it may be on the heap, it may be in registers, wherever. Right? So the stack frame, conceptually, is a portion of the information needed to manage this function activation, the calls and returns of the function. So what do I mean by a portion of the information needed? Well, depending on the architecture, the return address for a function may be passed on the stack, or it may be placed in a register. Okay? So how many of you have experience with Intel x86 assembly code? Okay, not many people. That's fine. So just an FYI, on the Intel architecture, so pretty much all the machines that your laptops and desktops have in them, on the Intel architecture, there's an instruction, a call instruction. So I say call, and I give it an address. That's the instruction. And what the call instruction does is it takes the address of the next instruction and pushes it on the stack. Okay, so the return address is pushed on the stack. What happens on the MIPS, though? You guys have the MIPS. Yeah, Steve.
That $RA.
What is $RA? It's a register. So on the MIPS, the return address is not pushed on the stack, it's placed in a register. So it's behaving differently. Now, the return address, when I make a function call, the return address is part of the information that I need to manage the activation of the callee. The callee needs to keep that return address around because otherwise it won't return properly. It won't know where to return to. So that return address is part of the activation record of the callee, but it need not be in the stack frame. On the MIPS it isn't. On the Intel x86 it is. On most RISC architectures, a call instruction, or on the MIPS it's the jump and link, right, JAL. Okay? So they may place it on the stack, they may place it in a register. There are some languages. So you guys have you had 372? So for example, in ML or Haskell, it's not a stack-oriented language. So the return address, I think, gets pushed in. The activation record gets created on the heap. Okay? So things that are different. So if we're studying compilers and we are prepared to deal with something more than just C, then it's important for us to understand that conceptually what's happening is when we make a procedure call, we save some information, right? And that's information that is saved may be on the stack, but it need not be. It could be in a register. It could be on the heap. So that's the reason I'm talking about activation records. I want to deliberately emphasize that a stack frame is a subset of that. So some aspects of the activation record layout. So for example, where do the actual parameters live? These are specified by the calling convention. Okay? So if you think about this for a bit, what happens is that within a function, so if I am a function and I have my local variables, well, it's no one else's business where my locals are. Okay, so I can keep my locals wherever I want. And sometimes, if a compiler is smart enough, some locals might only live in registers. Right? I may not need to actually allocate memory space for them. So this is for a compiler that's really smart. But if these are locals that I deal with and no one else gets to deal with, then it's my business where I place them. So no one else needs to know about it. I have complete control. Now, the formal parameters of a function are locals, but they aren't completely in my control, right? Because the values, the initial values of the formals are given by the caller. The caller defines the actual arguments. So the caller and the callee need to agree on where the formal parameters, the actual arguments, are going to be placed. Okay? So there needs to be some convention that the caller and the callee agree upon, such that the caller can place the arguments there, and the callee can pick them up from there, right? So that's the calling convention. Analogously, there's a return convention, which is that when I'm done, I have a return value. I need to place it someplace that the caller can pick it up from, okay? So this calling convention, which is external to the compiler, this determines the location and some machine state information. Where does the return address live? Okay. This is specified by the calling convention. On the other hand, for local variables and temporaries, we'll talk about temps a little later on. This stuff, which is independent of the calling convention because no one else needs to know about it, that gets decided by the compiler. And a couple of quick FYIs. One is that the amount of storage you need is determined by the type. Well, that seems fairly obvious, right? If I have an array of chars, well, if I have an array of 40 chars, then I need space for 40 chars. If I have an array of 40 ints, then I need space for 40 ints. So if I have an array of structs, and the structs, well, how big is each struct? And then, how many elements in my array? So the amount of space I need for a variable, or I'm sorry, for an object, is determined by the type, right? And this will ring a bell from your MIPS programming. Some architectures have alignment restrictions, right? So on the MIPS, if I have an int, a 4-byte quantity, what possible addresses can it take on? So here, I'll tell you this. On the MIPS, I generate a load instruction. I forget, is it called a move? It's called a move, right? Is it a move instruction or a load instruction? I think it's load, whatever. The thing that loads values from memory into registers. So I load a 4-byte quantity from memory address 10,003. Is that legal? Why not? It's got to be mod 4. It's got to be 4-byte aligned, right? So some architectures have specific restrictions on the alignment of variables. And why does the compiler care? Well, the compiler needs to be aware of these restrictions so that it can generate, it can allocate space for those variables appropriately. So if my compiler says, oh, look, here's a 4-byte quantity, and look, location 10,003 is free. Let's put it over there. Well, that's not good, on a MIPS at least. It would work fine on an x86. Here's what a stack frame for an x86 might look like. Here's the stack growing this direction. So here's the caller's frame up there. The caller's frame begins over here. The incoming arguments, the actual parameters, get placed by the caller over here. The call instruct. So in terms of the sequence of events that happens, the caller evaluates the actual arguments and pushes them on the stack. Then the call instruction happens. That pushes the return address over here. Then control enters the callee, and the callee says, oh, look, I need to save some registers. And the callee saves some registers over here. Then possibly the callee might save a frame pointer register, allocate its stack frame, and start execution. If it's going to make a function call, the callee now evaluates the actuals, pushes them on and so on. Okay, so that's what an x86 frame looks like. I thought I had a picture of a MIPS stack frame, but I don't. But that's all right. What sorts of allocations? Different languages may have different kinds of allocation schemes. So again, what the compiler needs to do, and as the compiler writer, something that you'd have to be aware of is to go and look at what kinds of allocation the language requires, and use allocation appropriately. So Fortran 77, for example, all storage is allocated by the compiler. Right? There was no notion of recursion. There was no dynamic memory allocation. Before GNU came out with Gawk, I used to write a lot of code in awk. And awk had static allocation, which is kind of annoying sometimes, but you could work with it. Gawk has functions and recursion, so Gawk now no longer has static allocation. So stack allocation is where activation records can be organized as a stack. So this is what you encounter in C, C++, Java, and so on, the standard stack model, right? But a pure stack model doesn't work if you have local variables whose lifetimes need to exceed the lifetime of the function, right? Because if I have a pure stack model, when I enter a function, that creates a stack frame or an activation record. When I leave the function, that activation record goes away. So all the locals go away. Well, that doesn't work if I have some variables and I need the values of those variables to stick around. So one gets around that by departing from pure stack allocation, saying, well, some things will get allocated on the heap. Right? And in some languages, you kind of go the whole hog and say, you know what, everything is going to get allocated on the heap. The reason Lisp and Scheme and Haskell and ML and so on have heap allocated activation records is that with stack allocation, a function activation essentially goes away when the function returns. Over here, I can execute a function a little bit and pass it as an argument to another function with Lisp and Scheme and ML and Haskell and so on. I can have these first-class functions called closures, right? And what that means is that the stack frame and variables in the stack frame don't have the simple last in, first out stack-oriented behavior. So I don't have a choice. I have to allocate them on the heap. Now, some languages allow you to pass procedures as arguments to other functions. So you can have function arguments, function objects as arguments. That's the crux of this thing over here. If I can take a function object and pass it as an argument, then that linguistic device has all sorts of runtime implications. So C kind of finesses that by saying we'll have function pointers. That's it, right? But function pointers aren't quite the same thing as first-class functions, the way Lisp and Scheme and ML have them. Yeah?
In that stack allocation strategy, when you're talking about locals that need to be retained when the activation ends, is that kind of like a static variable?
A static would have the same thing. Yeah. It's kind of confusing because in C, the word static is used in at least two different ways, right? OK, procedure calls and returns. So we're sort of slowly edging towards generating code. Okay, but we still need to know what needs to be done for managing activations. Again, just stepping back for a second for the code generation issue, there are two things. The compiler has to manage the code for each function. That's just code generation for the function. And it has to manage the interface between functions, the interaction between functions. Now, managing the interaction between functions is conceptually trickier than managing the code for an individual function. So procedure calls and returns, that is the interaction between functions. Okay? So that's what I'm going to be talking about now. Separately, we'll talk about how to do the code for a function. And now, if I know how to do the code for a function, and I know how this function is going to be interaction with other functions, and how the code generation for that interaction is to be done, then I'm done, right? Because now I have both inter-function interactions and intra-function code, and I'm good. So there are two pieces of code that I need to be aware of for handling calls and returns. One is called the calling sequence, and what the calling sequence is a sequence of instructions that manages the call from the caller to the callee. Okay? So what happens? What does the calling sequence do? It's a bunch of instructions, and what it does is it evaluates and puts the actual parameters where the callee can find them. That's important. And that's determined by the standard calling convention. And the calling conventions can get complicated. So for example, on most RISC processors, you have enough hardware registers that are visible that you can pass some arguments in registers. So that's more efficient than writing to memory and loading from memory. Okay, so you can pass some arguments in registers. But you have a fixed finite set of registers. So how many arguments can you pass in registers? Well, depending on how many registers, maybe 2, maybe 3, maybe 4, maybe 6 if you're really, really rich in registers. But the language has no upper bound on the number of arguments a function can have, right? So suppose my machine, the particular machine I'm compiling on, my machine allows 4 arguments to be passed in registers. And it says the first argument is in this register, the second one is in this register, and so on. And I come to a function, and the function has 6 arguments. Now what? Well, I need to pass those arguments somewhere, right? So typically what will happen is the calling convention will say, for that machine will say, arguments 1, 2, 3, 4 in these registers. If there are more, they get passed on the stack. Okay? So dealing with all of that properly is part of the responsibility of the calling sequence. Then the machine has to, the calling sequence has to save the machine state. It has to save the return address. Possibly it has to save some stack pointer registers, the old top of the stack. Then someone at some point needs to jump to the callee, right, start executing the callee. Somewhere it needs to allocate an activation record. Now, these are actions that need to be done. This is not necessarily in this sequence. It's not necessarily in this sequence. So for example, it's possible to allocate the activation record up here and then save the machine state in that activation record. Okay, so it's important to note that this does not imply a particular sequence of actions. It's the sequence of instructions that carries out a set of actions. Okay? The return sequence is the dual of this. It undoes the actions of the calling sequence by and large. So it loads the return value where the caller can find it. It deallocates the activation record. It restores the machine state. It branches back to the caller. Okay. Now, not all of that is done exclusively within the caller or within the callee. So in terms, if you think of a runtime trace of what's going on at runtime, here's the calling sequence, and some of it's in the caller and some of it's in the callee. Okay? The part of the calling sequence is in the caller and partly is in the callee. And this picture, don't take it too literally. This does not mean that half the calling sequence is in the caller and half of it's in the callee. Okay? So analogously, I have the return sequence. Some of it's in the callee. So the callee sets up the return value, if there's one, puts it where the caller can find it, deallocates the stack frame. Control returns to the caller. The caller might take the return value, put it someplace where it can find it separately. So here's the return sequence. And in between these is the actual body of the callee. Okay. So the calling convention, we alluded to this earlier, for an architecture and language, specifies how values are communicated between the caller and the callee. Now, one might think that, hey, I have all these functions in my program. I should be free to set up my, their argument passing any which way I like, right? And to some extent, that's true. To some extent, that's true. The problem arises, and the place where the calling convention kind of needs, where the code that the compiler generates needs to adhere to a fixed external calling convention. There are 2 places where that comes into play. One is anytime you're interacting with a library function, right? The libraries are pre-compiled. So for example, if you're generating code for some function and it calls printf, well, the arguments have to be placed at the right place so that when control goes to the library routine printf, it knows where to find the arguments. Okay, so anytime you call strlen or stringcat or malloc or whatever, anytime your program interacts with an external library, that interaction has to be mediated by the standard calling convention. Okay, so that's one place where a compiler can't say, well, I'll just generate code the way I want to. So that's one place. The other place, and this is again an interaction with a different sort of an external entity, is if what I'm thinking of is interactions with things like the debugger. Okay, so the debugger needs to know where to find the arguments, what the arguments are, and so on. So if you go into GDB, if you put a breakpoint on a function, when you hit the breakpoint, it'll show you what the actual arguments are, and it's doing that by looking up. It's essentially by using the knowledge of the standard calling convention to figure out how many arguments the function has. That it retrieves from the symbol table, and now it knows where the arguments are and shows you. Okay. It is possible to have multiple calling conventions. So you as a programmer can say, hey, you can tell the compiler, I would like this function to use this calling convention. So in Windows, you can have seat echo, standard call, and so on. And what these do, in effect, is specify how functions, how the arguments are, where the arguments live. So let me talk about one more thing, and then I'll stop today. Caller versus callee saved registers. So you have a machine, you have an architecture. It has some fixed number of registers. Okay, I think on the MIPS you have what, 32? I've forgotten. Okay, so you have 32 registers. So some of these are dedicated for the execution environment, the runtime execution, like the stack pointer. Okay, so you probably don't want to mess with that. You can, but be really, really careful if you do. So then there are others that are reserved. So for example, I think on the MIPS, there's the $RA, which is return address. That's what, register 29 maybe? I don't remember. Some register, okay. There's a stack pointer register. There's a register, I think A0 through A3 or A4, that are argument registers. That's where you pass the actual arguments. So then you have a bunch. Once you take away the registers that have, by convention, have specific uses, you're left with a set of scratch registers. Okay? And these scratch registers get divvied up. So let's think of how we might divide them up. Okay? One possibility is to say, okay, I'll divide these. I'm not going to do any dividing up. If a function wants to use these registers, any of these, it has to save the value in the register, and then it has to restore it at the end. So you think about that for a second. You say, well, that only makes sense if my caller wants that value saved. Right? Because otherwise, what's the point in saving it and restoring it? So suppose I do it this way. Suppose I say that the callee will save the value of any register that it uses, use that register, restore that register when it finishes. If I do that, so that's kind of nice for the caller. Because now the caller can say, hey, I can use any register I want. And if I make a function call, the callee is going to save any register that it touches. So I don't have to save the registers myself. So this is great. The downside to this, I mean, this sounds advantageous, but the downside is that the callee might end up saving registers that the caller doesn't care about. Right? So the callee says, oh, look, I need these 10 registers. I'm going to save all of them, use them. I'm going to restore all of them. And maybe the caller needs just one of them, right? It's using one. So there's a lot of wasted work that's happening. If the callee saves everything, regardless of whether the caller cares about those registers or not. So you could turn that around and say, well, tell you what, how about it's the caller's responsibility to always save any register that it wants to survive across a function call. Okay? And the callee doesn't need to worry about it. And this has a dual downside. You can construct some situations where that's wasteful. So what we'll do, and we'll get into this in a little more detail on Wednesday, what we'll do is we'll divide up the registers into some that are saved by the caller, and it's the caller's responsibility. And there are some that are saved by the callee, and that's the callee's responsibility. So as the name suggests, some are caller saved, some are callee saved. We'll get into that on Wednesday. Okay, so I'll see you guys then.